today is given by Professor Xiao-Gang Wen. He's going to continue his talk on symmetry-protected topological order and group cohomology theory. Let's welcome him.
Yeah, I'm sorry. I couldn't finish my my stuff in the given time, so I have to have this extra time. So it's kind of long day. Let me just summarize that. So in the last lecture this morning, we used a nonlinear signal model to describe so-called disordered phase, taking the limit which is lambda go to infinity. And this is very much like what Chenke talked about, and also what Chenke talked about. You start with some field theory, make field theory have a strong quantum fluctuation, and you make it a disordered phase. And but however, we find the field theory can give you disordered phase or symmetric phase, but you can get different one if you add a different topological term. So we can add some kind of winding number. You know, some winding number term. When you add a different topological term, actually this field theory is 2 pi quantized, so we put a pi here. So this different topological term would give rise to different gapped symmetric phase. And so classifying this topological term correspond to classify different gap phase, and that's how we get this table. But you may just wonder or may disagree with what I said, because why adding different term gave us different gap phase? You know, it's just you know, when you have a phase diagram, and for example, we have some phase diagram, and this is a gap phase. And you know, the effect is the theory for different point in the gap phase. They all described by different Lagrangian or different action. So when you have a different, you know, it's not clear why when two actions are different, then these two systems must be in different phase. So here we are facing the similar puzzle. You know, when you're choosing different topological term, how can you claim the different topological term correspond to different gap phase? By simply say, oh, these two Lagrangian are different is not enough, because these two systems, two ground states, probably can be connected without phase transition. You have to show that there is no path connecting two ground states without going through phase transition. You have to check every path, and this appears to be very difficult. You know, how do you know? Suppose you check one path, you say, oh, there's a phase transition, but how do you know there do not exist another path where there's no phase transition which connect two ground states? So this becomes difficult. And so the way to show that these two different this system describe different phase is to looking for some topological invariance, and that's what Chenke emphasized. Something physical, measurable. If you have some physical, measurable quantity, and if this quantity is quantized, and when you see that these two different Lagrangian give you two different quantized value, then you say, okay, these two Lagrangian probably do this correspond to different topological, different phase. And so this is a wonderful issue I'm going to start discuss now, is that we need to have some probe. If you claim you can use a nonlinear signal model or some other field theory to construct SPD phase or different SPD phase, then you need to find this some kind of a probe. This probe give you different value for different SPD phase, and then you're sure there are different SPD phase. Okay, and so there's a notion of a universal probe. That is, you can use in one experiment and probe all the SPD phase, just like the X-ray diffraction experiments. You can use in X-ray diffraction to detect all possible crystal order. So whether we have a universal probe which detect all possible SPD phase. And so one idea is to using this topological partition function. I actually this is some typo here. Is that so this is the full partition one, not topological one. And so the partition function of SPD phase actually have this form. You can easily see this because for every pass, the amplitude equal to 1. So therefore, total partition function just summing over many ones. But how many ones do we have? Because that's how many terms do we have. And how many terms do we have is that for each vertex, we have a variable, which is a group element. And we're summing over all possible set of group elements. So the total possible number of paths is a group element raised to the power of this NV is a number of vertex. Since each path is 1, and you have so many paths, so total partition function is 1 times the number of paths. So we see that you can see that total partition function have the form we described before. That is there is a volume term. So this term is linearly proportional to volume. So something e to the some number times the volume. Then there is a universal term here, and this universal term is what we call topological partition function. And in this case, topological partition function equal to 1. And for every possible topology for closed space-time manifold. So therefore, the idea we have to classify or to probe topology order does not work here, because for the SPD phase, the topological part of partition function, which is the volume independent part of partition function, always equal to 1, regardless what kind of space-time topology we have. So this is consistent with our desire that this nonlinear single model we construct actually describe a trivial topological order. So the kind of partition function equal to topological partition function equal to 1 is consistent with trivial topological order. But on the other hand, let's also say that we cannot use a topological partition function to probe different SPD phase, because all different SPD phase, they all have a partition function equal to 1. So we couldn't do it. We cannot using the partition function, this idea, to probe different SPD phase. However, we still like this idea, so we still want to use this partition function idea to probe different SPD phase. By the way, I want to say that this topological partition function actually is we believe is a universal probe for topological order. You know, for topological order, we can use this universal part of partition function to probe all topological order. This is a conjecture; it's not proven, but we kind of thinking that way. So in order to use this idea to probe SPD phase, we have to do something else. What we do is what Chenka talked about, which is introduced by Lavin and Gu. That is a gauging the symmetry. Because SPD phase have a symmetry, so we can gauge the symmetry. Once we gauge the symmetry, then the partition function for so-called gauged Lagrangian is no longer equal to 1. And then we can use this gauged partition function to probe SPD phase. So that's an idea. So what do you mean by gauging the symmetry? And remember the SPD phase is really defined in our construction. The nonlinear single model is really defined on the space-time lattice. So actually our action is given by the cocycles. I mentioned that there's a so-called homogeneous cocycle and inhomogeneous cocycle. Actually, the description I gave this morning using so-called homogeneous cocycle. And the gauging process actually is to go from homogeneous cocycle to non-homogeneous cocycle. So, but this is all kind of very mathematical. So I will not really go through that, but there is a process to do that. And here we will fall back to the field theory. So let's ignore this. Let's forget about this group cocycle definition of nonlinear single model. Let's go back to field theory. So you can see in the field theory what do you mean by gauging. In the field theory, the gauging is a more familiar concept. That suppose we have a field theory which is a function of G inverse dg, which is kind of like this term, and certainly this Lagrangian have a symmetry, because if changing G to H times G, H is constant, then plug this Hg to here, this H inverse cancel, so the Lagrangian do not change. So there's we have global symmetry. Then the gauging is that we assume H have a spatial dependence. If H have a spatial dependence, when we insert this transformed G into here, we find this Lagrangian change to another Lagrangian. So we have actual H inverse DH term. Okay. And the gauging simply is actually modify this Lagrangian further, replacing this H inverse DH term by some kind of some other connections. And then in this way, we transform a Lagrangian with just a G into a Lagrangian with a G and A. So we have this actual A. So this actual A is a multiplication of Lagrangian. So this Lagrangian gets modified, and there's a particular way to modify this Lagrangian by this this kind of rule of changing Lagrangian. Okay, and this modified Lagrangian is like turning on some probe. You know what do you mean by probing the system? Probing the system means we modify Lagrangian. Then how to measure the response? Is that when we modify Lagrangian, then the partition function for modified Lagrangian will be changed. Then we say, what is the change in the partition function because the change in the Lagrangian? So that will be response. So what we do here is very much like this response theory. We modify Lagrangian in a particular way, and we try to see, after we modify this Lagrangian, then we do the path integral over G, then to see how this modified Lagrangian produce a modified partition function. And then using this kind of modified partition function as a probe. And so this is so therefore once we have a modified Lagrangian, we can do the path integral. And again, similarly, the path integral would contain a term which is a kind of, we hope this universal term and a non-universal term which may depend on the volume. But in this particular case, we can have a more precise definition of the separation of universal or non-universal term. We simply divide the partition function of ungauged Lagrangian. So this ratio of gauged Lagrangian and ungauged Lagrangian contain only the topological term. So the volume term are cancelled out. Okay, and this is very important because the volume term is hard to determine, especially if there is no translation symmetry. If there is no translation symmetry, it's hard to say what do you mean by volume term. It's hard to separate the volume term and the topological term. But however, for this HPD phase, it's easier. We don't need to separate them. We just the ratio of a gauged Lagrangian and ungauged Lagrangian, and that's it. And this ratio presumably is the topological term, and so we usually write topological term as an exponential of some kind of action term, something local. And so we claim that this function depends on the connection on space-time. And this function, what depends on connection on the space-time, is our topological invariance. We want to use in this kind of topological invariance to detect and to probe SPD phase, and that's it. That's the main idea. And so this idea is very much like a topological order. In topological order, we want to change the space-time topology. Then the partition function depends on space-time topology, and we use that dependence to probe topological order. Here, we do not change space-time topology. But we add different symmetry twist. You know, this gauging is like a twist in the symmetry. We add a different symmetry twist to the space-time, or maybe adding different connection. This connection really describes the gauging or twist the symmetry. And then the partition function will depend on this gauge connection, and we use this dependence on the gauge connection to probe SPD phase.
So the whole thing will be labeled by the center of the H.
Hmm?
The whole thing will be labeled by the center of the H.
Center?
Of the gauge group, for example, SUN with the N.
No. So maybe let me to address this question. Let's just so this actually is this. And so actually I declare this term is universal, and there's this declaration is not quite correct actually. It's only universal in certain limit actually, and so which limit? So it's very important to say that this gauge field is kind of flat. So this gauge connection kind of flat. So if globally the gauge connection is a H inverse DH, then this is really trivial gauge, it's nothing. So therefore, if globally gauge connection have this form, then this ratio just equal to 1, because it's a really same path integral, just changing the variable. However, if locally the gauge connection looks like this, only locally, I mean locally is pure gauge, but globally it may not be pure. So that means the curvature of a gauge connection equal to 0. But however, we have a non-contractile loop in the space-time. Then around this non-contractile loop, this integration of a gauge potential may not be 0. In that case, we have a situation that locally it looks like this. But then you can say, one may say, okay, if it locally looks like this, the ratio should be also equal to 1. Because this system have energy gap, and all the correlation functions are short-ranged. So therefore, you may say that the system is nearsighted. They can only see the local property. If locally the gauge potential has this form, then we think that this ratio should be equal to 1. But somehow there is some, I don't know, some reason, and actually, if locally it looks like a pure gauge, but globally not pure gauge, this ratio is not equal to 1. And so this representing there's something non-trivial here. But I want to use this to argue that if locally is a pure gauge, this ratio, if not equal to 1, but should be universal. It should not depend on detail of the system, because locally it just looks like pure gauge, so we don't have much change. And then, but then when the gauge group is continuous, then there's a new situation. Is that we could have a situation that the curvature is very small, and but it's like a 1 over system size square. So basically, if system is very big, then the curvature is very small. Means maybe in the whole system you only have 1 flux, basically something like that. So if curvature is very small, in a large system limit, still locally things are flat. So in this limit, we still think, well, the curvature is not important. And so maybe this is still universal. So basically, this is two situations we are thinking about. Is that either this gauge connection is exactly flat, that's when the group is a discrete. For discrete group, we can require the gauge connection exactly flat. But however, for a continuous group, we can require this flux to be very small, but maybe non-zero. So we claim that in these two limits, in both cases, the gauge connection kind of locally flat. So therefore, this particular function in these two limits are universal. And the reason I emphasize these two limits is because the effective theory may contain something like a Maxwell term, like a f squared term. So trace of f squared term, f term. And then the coefficient may be non-universal. So this term is non-universal. But however, in the limit where this gauge connection is very, very small, and this kind of term probably can be ignored.
So I have a very dumb question. So A is taking A is a function. So you are integrated over a space-time loop, right? So how does A change from one end to the other when you go around 2π? Can you change by a lot, say integer multiple?
No, A is usually A is small. It's an integration of A on a large loop. It's something fine, order 1. So A is always order 1 over linear size of the
But I'm
system.
just trying to understand, is it different from people say large gauge transformation, that when you have A, going from x, A of x going to A of x plus 2π, say going on a circle, then A of x plus 2π then equal to
Yeah, but these two A differ by, I think A itself is 1 over system size is small, so in their integration is order 1. Is that so you say?
Yeah, is A a periodic function or not?
But A is a periodic function.
Yeah, is A a periodic function or not?
Basically, what I'm trying to, it's hard to say because A is a field. So indeed, there are some periodics that if you have two configurations, their loop integral only differ by 2 pi. Then we say these two configurations are equivalent.
I see. So this is not a large gauge.
Yeah, these are not large gauge transformation. The gauge are different. They are not large gauge transformation.
Question.
Yeah.
So what kind of probe? What you probe the response? What you probe the H state transport some path excitation by turning on this gauge field physically.
So what we actually idea is the following. So this is the idea is that when you gauge the nonlinear sigma model and integrate the matter field, you obtain some kind of effective theory.
Yeah.
But this theory is a theory for gauge connection. Although gauge connection do not fluctuate, but you get some kind of gauge theory. And then there's two kind of terms in the gauge theory. One kind of term depend on metric, so like this kind of term depend on metric. Those terms are not universal. But there is a topological term, like a chain-summon term or something, those kind of terms, they do not depend on metric. And those terms do not depend on metric are kind of topological. And so basically, we kind of separate those terms which do not depend on metric, like chain-summon term. And so then this topological gauge term is a non-trivial quantized response.
So it sometimes probe the H mode transport like the quantum H
It's probe many things, and the claim is that this kind of topological gauge term capture everything. So from there you can derive all the physical property, including H states, the statistics of defect, and so actually they are full calculation of SPD phase. So presumably, all the property of this SPD phase can be derived from this gauge topological term.
So you're saying so A contains some singularities, right? A also contains some.
A have no so here I try to say A have no singularity. All the curvature for A are very small.
Yeah, but if I view this integration over loop as a contour integral, then you need to have non-zero back. You need to have poles in there.
A do not have to be globally defined.
Oh, I see. Okay.
And those are really non-trivial vector bundles. So the A only depend on the patch by patch wise defined.
I see what you mean.
And so I already mentioned that so we have this gauge topology. So how to derive this gauge topology term? And actually it's pretty simple. So we have nonlinear sigma topology term. So that's what you write down. This topology term we write down before is a nonlinear sigma topology term, and which actually correspond to this cocycle. But I already said that let's use in field theory, which is more familiar. We don't use cocycle. We use a nonlinear sigma topology term. And then to obtain nonlinear sigma topology term, we can easily obtain the gauge topology term by simply replacing this G inverse dg in the nonlinear sigma topology term by A, and that's basically we get the gauge topology term. So that's kind of a cheaper way to get that. So let's consider example. Remember this for the H2. For the H2 SPD states, our nonlinear sigma topology term actually is here is a differential form expression. That is G inverse dg is one form, cube that gives us a 3 form, and this is a matrix, a trace that gives us a 3 form, real 3 form, not matrix valid 3 form. And then this the integration of the 3 form corresponds to this gauge topology term. Okay. And correspond nonlinear sigma model topology term. Okay, then we want to add this SU2 twist, and then adding SU2 twist gauging that, the integrate out the G, and what we get, the gauge topology term we get a response actually simply replace this G inverse D by this A. A is again is one form, it's a connection one form, and then we do that we get A cube. But however, this is okay if A is a pure gauge. Okay, if A have a non-zero curvature, then actually this term is not gauge invariant. But then we know how to make this gauge invariant. We just add this 3AF, and this combination have to be a Chern-Simons term. So this combination is a gauge invariant even when the curvature F is non-zero. So basically that's our way to guess. So we claim that if you gauge this topological term and integrate out the matter field, we should get this gauge topological term. So that's the conjecture. And so that's how we get this gauge topological term. And and this gauge topological term is very simple for the S2 SPD state in 2+1 dimension. It's simply the SU2 Chern-Simons term.
I think we can actually calculate that.
I don't know actually. We tried.
Fermion.
Oh, using Fermionization? Yeah, that's probably true.
Yeah, we can actually calculate it.
Without using Fermion, it's a little bit tricky. And using just do the bosonic path integral is a little bit tricky. I don't know how to do that. So here I have to wave my hand to say, yeah, this thing. But however, it's very much like what we did before for the invertible topological order. So actually, you can see that you know, in the morning lecture, we try to classify this topological term, try to obtain different SPD states. And here we can classify this gauge topological term, using gauge topological term to obtain SPD states. Because for SU2 gauge theory, in 2+ dimension, the only thing we have is a Chern-Simons theory. And then so that's the existing Chern-Simons theory. That means we may have this Chern-Simons theory can be the response of a gauged SU2 SPD states. So this existence of the non-trivial response suggests that existence of non-trivial SPD phase. And so that's basically this table. That's if you think about other dimensions, and it looks like we can only write down this Chern-Simons theory, the non-trivial gauge topological term in 2+1 dimension. And so therefore, that's the only thing we have. And actually, you may say, do you have a 0+1 dimensional topological term? In some sense, yes, because the Chern-Simons theory, Chern-Simons term in 0+1 simply just A, not AF. But this A is 2×2 matrix of SU2, so we have to do the trace of A. So actually, indeed, the trace of A is a potential topological term in 0+1 dimension. So we could have a non-trivial state here. But however, for SU2, the connection 2×2 matrix is traceless. So trace of A always equal to 0. So that's why we don't have it. But for U2, if the symmetry is U2, then the trace is non-zero. So actually, for the U2 symmetry, indeed we have something here. So using similar argument, you can see that in 2+1 we have something here. I think the next one is probably is 6+1. We may have some extra. So therefore, using this idea, we can study the gauge topological term. And if you have a gauge topological term, then that suggests that we have non-trivial SPD phase. So instead of say when you have a non-trivial nonlinear single model topological term, we have a non-trivial SPD phase. And here we say when you have a non-trivial gauge topological term, we have a non-trivial SPD phase. And the gauge topological term and the nonlinear single model topological term have this one-to-one correspondence. So that's why these two pictures basically are equivalent. We get the same results.
There is a Chern-Simons term, SU2 Chern-Simons in 4+1, right? So there should be another term in 4+1.
4+1.
Yeah, there's a Chern-Simons term 4+1 for SU2.
Yeah, there's an A wedge F wedge F.
A wedge, that's a non-zero?
That can be non-zero. So why do we care about finite dimensions?
If it's non-zero, may have a, let me see, A wedge F, wedge F. I'm worried about that's for SU2. Yeah, there are one, but for SU2 that's maybe not zero.
That could be 0.
Yeah, that's 0.
So SU2
In general, they are non-zero, but for SU2 they are 0 because you need the 4F to be.
There's no chiral anomaly for SU2.
Yeah. So in general, for